Hello, everyone. Thanks for joining us today. Today, we are pleased to have Dhruv. You might already know it. He gave many talks here. He did several excellent work in RA theory. He's a final year PhD student at MIT, advised by Ankur Moita. His research focuses on understanding fundamental building blocks of machine learning and fitting them together to solve more complex problems, in particular sequential decision making. And today we will see his last work, I guess, inspired by this time RL in LLM. Thanks a lot for accepting our invitation, Dhruv, and the stage is yours. Thank you.
Thank you. So thank you all for coming, and thanks for the introduction. So this work is about the role of foundation models in efficient reinforcement learning, and in particular in exploration. And this is based on joint work with Dylan Foster and Zach Mamidi. So I will start this talk by giving two complementary motivations for the problem that we study that sort of fit together. One of the motivations is how we can improve the sample complexity of post-training language models. So the standard large language model pipeline has a few different phases. The first is typically some sort of pre-training, where you have a huge amount of data and a huge amount of compute, and you do some supervised learning to give some initial model. Then there's post-training and inference time. So the focus of this talk will be on this post-training step, where you have more limited compute, and you have much more limited data also. And you want to do some sort of reinforcement learning to improve the quality of your model for some specific tasks or family of tasks. And the way this works here is you no longer have some demonstrations of problems and solutions, but you have the ability to ask for a problem, propose a solution, and then receive some reward. So this is the standard reinforcement learning setup. And you might care about how many interactions with the evaluator you need, as well as how much compute you're using in this phase. So what do people do for post-training today? There's a few different families of algorithms. One of them is for reinforcement learning with human feedback, which is sort of this problem of learning from human preference data. So here you'll typically either fit a reward model to the preference data and then optimize this reward using reinforcement learning, or you can directly fit your language model to the preference data. And this is the algorithm known as direct preference optimization. The second paradigm, which I'll be more concerned with today, is reinforcement learning with verifiable rewards, which just means that you have some direct rewards from some verifier. You don't need to train a reward model. And these are numerical rewards. These are not some sort of preference rewards. So there's a variety of examples where you might have verifiable rewards. These could be unit tests for code. These could be formal proof checkers for math, or this could be a human evaluator. Like your language model is trying to solve the Riemann hypothesis, and you have some mathematician who can check if this proof is legitimate. So there is some empirical belief today that reinforcement learning, and in particular reinforcement learning with verifiable rewards, has the ability to unlock complex reasoning behaviors that maybe the base model did not already possess. However, there's also some empirical evidence suggesting that this is not the case, that in some sense, current RL methods are just maybe amplifying behaviors that are already present in the base model. So what does this concretely mean? Well, the evidence is sort of the following. If you have some problem that can be solved with at least like a 10% chance by your base model, and you amplify this so now you're solving it with 90% chance, that's a good win, but in some sense you might say that the base model was already fairly good at being able to solve this. And so these plots here are showing these sort of Passett K curves, which suggests that reinforcement learning is amplifying the probability of behaviors that are already fairly likely, but it may not be doing more than that. And so this is, roughly speaking, the current state of affairs. And this raises the question of, can we do better than this? Can we get models to discover truly novel behaviors in post-training? And what I mean by truly novel is maybe behaviors that were quite rare for the base model itself to be able to perform. And maybe one hope is that we can achieve this if we are more efficient about data usage. Maybe the amount of data we have and the algorithms that we have are just not enough. Maybe the algorithms are not efficient enough to be able to discover rare behaviors. So in some sense, this is the perspective that we've been pursuing in classical reinforcement learning theory and practice for many decades. Because we know in theory that there are algorithms for reinforcement learning that do some sort of active exploration, and they can learn behaviors that would have been exponentially unlikely under the initial policy. So in classical reinforcement learning, there is no base model, but you can think of the base model as sort of the uniform distribution over actions, sort of the uniform prior. And in that case, we know that you can learn behaviors that the uniform policy is exponentially unlikely to perform. So the sample complexity of learning with active exploration can be exponentially better than learning with passive exploration. This is maybe like the central like theoretical cornerstone of reinforcement learning. For example, we know that in tabular Markov decision processes, if you do some sort of standard greedy method, you might need an exponential number of episodes in the horizon in order to learn. But we also know that with better algorithms, it's like you can get away with only a polynomial number of episodes. So there's a huge win in sample complexity here for tabular MDPs. And in the case of tabular MDPs, these algorithms are also computationally efficient, so this is as much as you can hope for. However, when you move beyond tabular MDPs, the question of computation and runtime becomes much more subtle and typically much more pessimistic. So as I will discuss later in more formality, the computational complexity of reinforcement learning methods that use active exploration can be much, much worse than the computational complexity of reinforcement learning methods that are sort of doing some sort of passive exploration. And this will hold even in very simple toy models. So as theorists, this is just fundamentally unsatisfying if our algorithms are not provably implementable, at least in very simple settings. For example, maybe you can't do optimization in full generality in non-convex settings, but at least we have some theoretical toolbox saying that in convex cases, we can do optimization. And then maybe from a practical perspective, we might also believe that computational complexity provides some lens on things that might be easier and things that might be harder in practice. So that's some motivation for this question of computational complexity. And this ties us into our second motivation, which is, can we leverage the base model to do exploration faster in reinforcement learning? And by faster here, I mean better runtime. So what's the state of affairs of computational complexity in reinforcement learning? It's fairly grim, because the most general statistical guarantees, in other words, the guarantees that work under the most general assumptions on the environments, these are achieved by algorithms that are doing some sort of exhaustive enumeration. They're doing some sort of brute force search. So the examples of these are algorithms like Olive, which use global optimism. And there's sort of no hope of implementing these efficiently. And there's also some fundamental computational barriers saying that maybe we cannot hope to get provable fast algorithms for reinforcement learning. And as we'll see, even in reinforcement learning for language models, where you have this pre-trained language model to help you do reinforcement learning, existing methods for exploration seem to be computationally intractable. It's not clear how to implement them efficiently, regardless of how strong the base model is. And so the question here is, to what extent can powerful base models alleviate this computational challenge? Can we leverage the base model in some sort of fine-grained way, depending on how good it is, to get faster algorithms? To get faster algorithms.
Yeah, I have a question here. So I guess computation is one side, but for the for the most generic guarantees you're talking about,
yes.
I think there may be even a problem on the statistical side, right? So for the guarantees achieved by Olive and other algorithms, you need to assume things like bounded Bellman rank and bounded Bellman-Eluted dimension, like things of that sort.
Yes.
And I think typically in fairly speaking, like those are pretty strong assumptions. Like sometimes you probably don't really expect them to hold in practice. So like I think the way I understand like the SLAM work, like which I really like by you and Dylan, is like sometimes in reality, like exhaustive exploration, even if you ignore computation, is probably like a dead end, even statistically to begin with. And with base model, like you maybe have a hope is like you can do some local exploration just within the coverage of the base model.
Yes.
And then that combines with the computational advantage, but it gives some like a promising path. But I really think like there are two separate things here. One is you want to aim at something that is statistically plausible without strong structural assumption on the environment to begin with. And then there's also the computational aspect.
Yeah, so I definitely agree that like you could hope for things, or you could say like the Bellman stuff is still not general enough.
Right.
I guess, yeah, I have like a few thoughts on that maybe, but that's like maybe a bit more tangential. But I definitely agree with you. Yes, like the hope here is like do things sort of within the coverage of the base model, and like what all can you do?
Yeah, right. I think maybe another way to put it is like compared to those like general guarantees, you're also changing the sort of the statistical goal, or it's like the assumptions behind the statistical guarantees. So change that from those general like rank type structural assumptions to say, oh, I have the base model and I'm happy to just live within its coverage or things of that sort.
Yeah, yeah. I guess maybe we can come back to this sort of when I explain what the results and assumptions are, and then we have more context. Yeah, but good question. So this gives us basically two motivations for what we're going to study in this work. One of them is improving the sample complexity of standard empirical algorithms for post-training. And one of them is improving the computational complexity of the sort of RL theory algorithms by actually leveraging the base model. And we'll see these are sort of like two motivations for the same question. So to outline the rest of this talk, I'll start by discussing maybe the standard framework, the statistical framework for language model reinforcement learning, which has emerged in the last few years. And then I'll discuss how we can turn this into a computational framework in a toy model of what we'll call these softmax linear models. And I'll discuss what existing algorithms look like, what guarantees are achieved by existing algorithms in this toy model. And then I'll talk about our results. So that's the general outline. And I'll start with the statistical framework. So in language model reinforcement learning, we have a language model. It's just a distribution over responses given prompts. Now, the response space is, of course, huge. It's exponentially large in the length of text that we can allow. And for the first part of this talk, I will be ignoring the sequential structure in the response space, and I'll come back to this later. But for now, we should just think of this as some huge response space that we cannot enumerate over efficiently. And the way we have of accessing this response space is some base model, which we'll call PyBase. So this is a language model. Now, the typical reinforcement learning process in practice looks something like this. It proceeds in some sequence of iterations. You draw some data, you sample some responses, and you get the rewards for these responses for the given prompt. And then you do some computation, maybe you update your model and proceed. So this fits very nicely into a contextual bandits framework, where you proceed over some number of iterations, you receive a prompt, which is just the context, you pick responses, which are just the actions, and then you query the rewards. Now, the standard goal in this reinforcement learning setup is to learn a model, pi-hat, that approximately maximizes the KL regularized reward. So in standard bandits and contextual bandits, you just want to maximize reward. In this setting, we care about not straying too far from the base model that we pre-trained. We sort of don't want to lose the capabilities that it had. And so we regularize our objective towards the base model according to some parameter beta and measured by KL divergence.
So regarding that, like, do you think? So I've always wondered because this whole narrative sounds to me like the KL regularization should be part of the method, but not part of the final goal. Where you may say like eventually, at least in the mathematical formulation I still only care about the plain rewards, but as a method, I may add irregularization. But somehow that's not usually how things are formulated. Usually, in all those problems, we just treat KL as part of the final objective. Like, what's the maybe as what you said is maybe KL avoids the post-trained model it helps avoid forgetting the base capabilities, but
Yes.
and that part may be hard to capture in our mathematical formulation. Is that the reason we keep it as part of the final objective instead of treating it as an intermediate learning method?
Yeah, I mean, that's a good question. Like, I think it would be very interesting if you could maybe formalize some notion of it's sort of it's really sort of a multi-objective problem post-training, right? And I don't really know a clean formalization for that. I think that you can get out unregularized regret guarantees from this in terms of beta. And so this is in some means just a method of achieving unregularized regrets, but I don't recall the formal specifics of that.
Well, I mean, okay, Chaba has a hand up, but if you have any guarantee for beta, you can always tune beta to get guarantee for plain reward. But usually, if you design your algorithm to get good guarantee under KL regularization, it may not necessarily give the best plain reward guarantee. I would guess it differs in terms of what you treat as your final objective when you write down the theoretical analysis. Right?
Yes. Yeah. It depends on beta. Yeah.
Chaba, you had a hand up.
Yeah, I think you said it right, Dhruv. This is a multi-objective problem, and you can have a clear formulation. You want to be good at the pre-training task and good at the fine-tuning task. And generally, these tasks are compatible with each other, right? It's not even like that there must be some trade-offs or something. Because the pre-training generally just says that, be good at language. And the other one is just saying that, on this specific aspect of the problem, you should be good at. The underlying intention is that these are compatible with each other. So to me, the scale regularized framework is trying to capture a little bit of this, but is it doing it in a good way or not?
I think KL is a very vague way to capture how much original capability you have maintained, right? But maybe it's a reasonable one given what we have now.
I mean, you wouldn't do this if you could access the previous task too, right? You have so many other things that you can do.
Yeah, if you knew what pre-training, what it really meant to capture the pre-training, then you could do something better. But I don't see what that actually is.
This is a shortcut.
Yeah. Okay. So in the standard statistical framework, you need some assumption that you have some policy class containing the optimal policy. And then once you have this, you can just talk about statistical complexity, which is measuring the number of reward queries that you need to learn a near optimal policy. So this is sort of a complete picture if you just care about the statistical angle of things. But this framework is too general to get interesting computational guarantees and to talk about computational complexity, because we have this huge response space that we have no way of accessing. And we have this abstract policy class that we have no way of optimizing over. So in the next part of the talk, I'll discuss how we can introduce some more specific framework where we can actually talk about computational complexity. So that's these softmax linear models. And they're defined as follows. We have a parametric policy class pi specified by some parameter theta. So the policy pi theta has density proportional to the base model times exponential of something that's linear in some d-dimensional feature map phi. So it's exponential of the inner product between the parameter theta and some feature phi of your prompt and your response. So if you make theta larger, you're sort of tilting farther and farther away from the base model. If you make theta equals 0, then you exactly recover the base model. So for this policy class, what you can observe is that the assumption that the optimal policy pi star was for the KL regularized objective was contained in this is satisfied if and only if the rewards satisfy essentially some linearity property. There's a shift, but we're not going to talk about this shift. And the proof is just that the optimal policy for the KL regularized objective is proportional to the base model times exponential of the reward, times this tuning parameter beta. And so if you make the reward linear in the features, then this is indeed a softmax linear policy, and vice versa. And in this talk, for simplicity, I'll focus on the special case where the rewards are actually linear, so there's no shift of any kind. And this makes things a little simpler.
Do you really need this shift? Because can't you just, isn't just linear generally enough that you can encode f star x as a dimensioning feature map?
Yeah, linear is enough, but I'm just saying that shift linear is also fine. Like,
I'm saying shift linear is a special case of linear.
Oh, if you just put it into your map somehow.
Yeah.
Yeah, sure. That's true. Yeah. If you're willing to change
I guess, but in practice, in terms of like what you actually model, there may be a difference. It's like you're saying like when we write down the model, maybe we don't need to model the shift part.
Yes, that's right. So that was the policy class. And we also need some way of accessing the response space. So in the standard bandit literature, it's very common to have some sort of optimization oracles. So you give some response y, or you place some response y with some prompt x, and you want to solve the maximization problem, inner product of theta with phi of xy. However, if you think about language model applications, this is not really reasonable. It's not really reasonable to perform any sort of exact optimization over the space of all possible text. So instead, we'll consider sampling oracles. And we'll consider two types of sampling oracles. The weak sampling oracle is just that you can sample from the base model. This is sort of obviously something we can do. For any prompt x, you can sample from the conditional distribution given that prompt. The strong sampling oracle, which is a bit more subtle, is saying that for any prompt x and for any policy pi, you can sample from that policy pi conditioned on the prompt x. And we'll assume that the base model lies in the policy class, so this one indeed supersedes the weak sampling oracle.
Also here, the policy pi that you're sampling from really shouldn't be arbitrary, but something that you can efficiently construct from your algorithm, right?
Yes, so ideally you like the thing that makes most sense in practice is really just the weak sampling oracle. Right. But the strong one will be useful to like state some different results.
But no, for the strong one, like if you're doing training, you gradually like improve your policy. It makes a lot of sense to be able to sample from the latest version of your like fine-tuned policy, right?
Yes, in some sense. Like there's like it becomes more subtle when you're trying to talk about like explicit computational complexity, because we're not like actually fine-tuning a transformer model in this setup, but yeah.
Oh.
Yeah. Like there are definitely algorithms in practice that do sort of assume the strong sampling oracle because they're doing exactly what you said.
Mm-hmm. Okay.
So now we have the statistical efficiency metric, and we also have a computational efficiency metric. When I say statistical efficiency, I mean how many reward queries am I making? How much interaction do I need with the evaluator? When I say computational efficiency, I just mean total runtime, including sampling oracle calls.
And so regarding that, so here's a very practical, maybe you're getting to that, but let me maybe ask that quickly anyway. Because if you're in an RLBR setting, like both of these are really computational in their nature.
Yes.
Right? And so the question, I think maybe what you're getting at is like, which one is more expensive? So you're saying like in practice, like the evaluation is much more expensive than like rolling up?
So I would not claim that's always the case. I think in many setups, like they're probably like, I don't know, like they're just both language models or something, so maybe they're comparable. Right. But definitely in this talk, we're motivated by like hopeful applications where the evaluator is sort of very expensive. If you think of like an actual mathematician, like
okay, so that would be like yes, that would be like just order. Yeah, I think in that case, it's fair to call even that call that a statistical because it's totally different in nature. Yeah.
Yes. Yeah. So yeah, that's why we'll think of statistical efficiency as maybe more expensive than like the computational complexity. And so now we can ask like, what is the statistical and computational efficiency of existing algorithms in our framework? So let's start with direct preference optimization. So direct preference optimization is of course stated typically in terms of preference rewards and not direct rewards, but it gives a very natural algorithm when you have direct rewards. You just draw a prompt, you draw a pair of responses, and you evaluate the rewards on each of those. And you solve some regression problem where you're regressing the rewards onto log density ratios. And you can check that this is sort of in the statistical limit of like large data. This gives the sort of policy that you want. And this simplifies quite nicely in our softmax linear setting to some sort of least squares. You're regressing a difference in rewards in an ordinary least squares fashion onto the difference in features. So this is just linear regression. And if your rewards are actually truly linear in the features with no shift, then you can even simplify this a little bit. And so this is the version I'll talk about in the rest of the talk. You're just regressing a single reward onto a single feature. So this is ordinary least squares at its simplest. And this is this is one of the cornerstones of how people implement post-training today, is direct preference optimization, which we'll think of as least squares. So here's the pseudocode. What you can show is that the statistical complexity of this algorithm will scale with the all policy coverage coefficient. So this is the worst case over all policies in your class of the density ratio between that policy and the base model. So for this to be efficient, you need that the base model covers every single policy in your policy class, which is not great. The computational complexity is, of course, no better. It cannot be better than the statistical complexity, but it's also not much worse. So it's polynomial in the feature dimension and the all policy coverage coefficient, just because you're solving a complex optimization problem. You're solving linear regression.
So in this case, all your policies are linear softmax, right?
Yes.
So wouldn't you be able to get a bound on C or control it by
X of 1 over beta.
Yeah, right?
Yes.
Okay.
But
is there what's the reason that that's considered like bad?
Yeah, that's considered bad because you want beta to be small enough that you can actually see rare behaviors.
I see.
Yeah.
Okay.
Like behaviors don't occur in your base model that often. So this is the standard direct preference optimization. You pay for the coverage in both statistical and computational complexity, and it's the all policy coverage coefficient. Now, there's a slightly more sophisticated algorithm called iterative DPO, which can slightly improve this. So here the algorithm is you just do DPO, but then you use the policy you learned to gather new data and you repeat some number of times. And what one can show is that now the statistical complexity scales only with a single policy coverage coefficient and also the feature dimension. So the single policy coverage coefficient is the density ratio between the optimal policy and the base model. So this, again, we are going to think of as fairly large. Ideally, we would not like to pay it. The computational complexity here, again, is roughly the same as the statistical complexity, because you're just, at every iteration, you're solving some efficient optimization problem. However, one caveat here is that this does require the strong oracle model. You need to sample from different pi thetas, not just from the base model. So that's the state of affairs for sort of practical algorithms. Now let's turn to some maybe RL theory algorithms, namely XPO. So this is some recent work where they take iterative DPO and they modify the objective at each iteration slightly. It's a little opaque what exactly this modification is doing, but one can show that it's behaving essentially like an optimism term that's incentivizing exploration in some way. And as a result of this optimism, this sort of active exploration, one can show that XPO achieves statistical complexity polynomial in the feature dimension, regardless of the coverage of the base model. So this is very good. This is basically the best you can do in this setting, up to polynomial factors, of course. Unfortunately, it's not clear how to implement this efficiently. The optimization problem is now non-convex. And so if we try to implement it, it's not clear how to do this without brute force search, which would take time exponential in the dimension. So that's the downside of this algorithm. So in light of these baselines, our question is twofold. First, can we improve the sample complexity of the passive exploration algorithms so that we don't pay for coverage in the samples? And can we do this without sacrificing runtime? And on the flip side, can we improve the computational complexity of the active exploration algorithms, such as XPO, by leveraging the base model? So notice that the guarantees of XPO did not actually change depending on how good the base model is. Can we leverage the base model to do better? And what I'll show in the next part of this talk is you can do better. You can sort of get the best of both worlds with sample complexity independent of coverage and computational complexity that scales with coverage but is no worse. So that's this algorithm that we'll call spanner sampling. Here's the slightly more formal guarantee. It learns an epsilon near optimal policy in the KL regularized regret sense, where the number of reward queries is polynomial in the dimension n1 over epsilon, and the overall runtime is polynomial in the number of reward queries and in the coverage C star. So that's the single policy coverage. And for this theorem that I'll state here, it works in the strong oracle model, but I'll get back to that later. So compared to the passive exploration methods like iterative DPO, we've pushed the dependence on C star from sample complexity to just runtime. And compared to XPO, we've avoided non-convex optimization, so we get a provable runtime guarantee. And moreover, this runtime guarantee improves as the base model gets stronger, which is intuitively what we would like to see. And later, we will show that this dependence on the runtime is actually necessary without further assumptions. So here's the intuition. If the base model has poor coverage of the optimal policy, so C star is large, then we do somehow need to draw many responses, many candidate responses, but we don't need to ask the evaluator for rewards on all of these. Instead, we can use the structure of the rewards, the sort of linear structure in the features, to prune a large set of responses to a smaller, more representative set, which we'll call a spanner, and then only query the rewards on the smaller set. And we're using this feature map fee to guide us in how we prune. Now, one thing I want to point out, just for context, is that in comparison with the sort of standard contextual bandits literature, this is going to be a spanner in sort of an average case sense, and not sort of a uniform sense. And the reason is because we only have access to sampling oracles rather than optimization oracles. So we really can't hope for constructing a uniformly good spanner. Okay, so here's basically what the algorithm looks like. There's two phases. The first phase is the spanner phase. It looks maybe like what you would expect. You draw some samples, you draw a sample from the base model. You check if its feature is in some direction that you've sort of not explored according to the elliptic potential. And if it's in this unexplored direction, then you query the rewards and you add it to your spanner. Otherwise, you don't query the rewards and you don't add to the spanner. And you do this a bunch of times. You do this T sub span times. And this gives you some set of data, which sort of is hopefully covering the feature space well. And then the regression phase is to just run iterative DPO as before, except using this data you've collected as a warm start. And the key facts here are that if you make T-span, the number of iterations in the spanner phase, roughly as large as the coverage coefficient, you can show that in the feature space, your spanner is roughly covering the optimal policy. And if you can show that the spanner is roughly covering the optimal policy, then you can show that the regression phase succeeds with a small number of iterations.
Here, when you say covers, I guess you're no longer measuring coverage by density ratio.
That's correct. I'm measuring it in feature space. I'll show that.
Right.
I'll show on the next slide exactly what that means.
Okay.
Yeah. And the third thing is to show that the number of reward queries in the spanner phase is not too large. And you do this using the elliptic potential lemma to argue that you're only sort of adding polynomial in D number of things to your spanner. So let's look in a bit more detail at what the guarantee looks like. So the main guarantee of the spanner phase is just saying that if you run it for t-span iterations, even if t-span is super large, the size of the spanner stays bounded by roughly the dimension d. And also, the uncovered probability decays like 1 over t-span. So uncovered probability, what I mean is the probability of a response under the base model that the feature of that response is sort of uncovered, like the elliptic potential with respect to your spanner is large. So it's in some direction that's rare in your spanner set. So this decays like 1 over t-span. So the reason this lemma is good for us is, first, we can bound the number of reward queries by the size of the spanner. And second, if you take t-span to be roughly c star, the coverage coefficient, then you can bound the probability, the uncovered probability under the optimal policy. So this is what I mean by coverage. This is like a sense in which we are approximately covering pi star beta, the optimal policy. So under responses drawn from the optimal policy, their feature vector is in a direction that's well covered by the spanner. And you can show that under this condition, where you have good coverage of the optimal policy in this average case sense, then the regression phase will succeed with only polynomial and d iterations. So the key point here is that if you run iterative DPO from scratch, it takes like c star iterations. But because we have this warm start, we only need polynomial and d iterations. So that was an algorithm that works in the strong oracle model. Just to remind you, the strong oracle model requires that you can sample from any policy in the policy class. The weak oracle model only requires that you can sample from the base model. And the reason we needed the strong oracle was because iterative DPO needs the strong oracle. It's sampling from arbitrary policies pi theta. Now there's a subtlety here, which is that if you were to try to like take our algorithm and implement it in practice, you have a base model, which is a language model. Obviously, you can sample from it. But now you're just tilting it by some exponential of some linear function. It's not at all obvious how you would in practice sample from pi theta. So it's not really clear if we should be assuming that we have access to the strong oracle.
Oh, so what if you just do rejection sampling?
Yes, that's a great question. So the first idea would be to just implement the strong oracle with rejection sampling from pi base. And the issue is just that now we're paying for all policy coverage in our computation. Because for arbitrary policies pi theta, we need to run rejection sampling. But it turns out you can, in fact, avoid this. And our solution is to basically do some sort of truncation of the linear softmax policies. So if you sort of truncate your policies according to the coverage defined by the spanner, you can show that for all the thetas that you care about, that are sort of like close to theta star, the density ratios are bounded roughly by the single policy coverage coefficient, at least in some like average case sense. And so with this truncation, then you can essentially implement the strong oracle with rejection, with approximate rejection sampling. And so this shows that you can actually implement our algorithm in the much more reasonable weak oracle model. So that's one extension. Two others I'll just briefly mention. One is that you can get not just the reward queries to be independent of C star, but also the number of sampled prompts. So you can think of many settings where you might only have some limited set of prompts available. And in those cases, you might care that the number of sampled prompts is not too large. And a third extension is you can get some sort of fast rate. Instead of 1 over epsilon squared, you can get 1 over epsilon, essentially using the fact that we're solving a regularized problem. And this turns out to be important for the multi-turn algorithm, but I'll probably not say more about this. Okay, so that was spanner sampling, which showed us that we can get our are statistical complexity independent of coverage, and are computational complexity to scale polynomially to coverage. But of course, this is not this is not the end of the story, because you would hope to ideally avoid paying coverage anywhere. Like, you might think of coverage as quite large. One thing we can show is that without structural assumptions, without additional structural assumptions, you cannot do better in some sense. So actually, even in the strong Oracle framework, any algorithm needs runtime scaling with C star, unless it's doing exhaustive search in some other way. The basic idea is just that you can construct an example where the base model is putting very, very small mass on some response Y star, and the rest on some null response. And you can construct a reward that favors Y star heavily in such a way that the optimal policy is going to put a constant amount of mass on Y star. And then there's just sort of nothing you can do. You have to find Y star, but the only ways you can do it are either exhaustively searching the space of responses, or exhaustively searching the space of policies, or drawing enough samples from the base model that you see this response Y star. And that's basically the sketch of the proof. So this is kind of disappointing, even if it's not too surprising. It's kind of disappointing because in language model applications, C star is measuring sequence level coverage. So this is the density ratio between the base model and the optimal policy. It's like, how much more likely is the optimal policy to produce some extremely long sequence of text? And so you can imagine that this might generically be exponentially large in the length of generations h. So in this part, we're going to discuss if we can do better with additional structure. In particular, we need to revisit our choice of policy class to actually exploit the fact that we're working in an autoregressive setting. So here we're going to talk about the response space for our language models being the space of sequences, where the tokens live in some token space A, and the horizon is some fixed h. So we're considering fixed length h sequences with tokens coming from A. Our original definition of softmax linear policies was this tilting of the density at a sequence level. So you multiply your density, your probability of some sequence, by this exponential. And while this was useful in the sense that realizability is very easy to interpret in terms of what the rewards have to satisfy, it's computationally annoying because it's not clear how to sample from pi theta star without paying for sequence level coverage. So this is an issue we had earlier. If you want to, even if you are able to learn the optimal policy without paying for sequence level coverage, like, how would you actually sample from it using the base model as a primitive? This is not clear. And the issue is that the optimal policy doesn't actually have this autoregressive structure that the base model had. Because you're tilting at the sequence level, you sort of messed up the partition function, and it doesn't necessarily decompose as you would like. So this motivates a new definition of a policy class that's specific to this autoregressive setting. And this is the autoregressive softmax linear policy class, where we define every policy in the class explicitly to have some autoregressive structure. In particular, we define the next token conditional distribution of some policy pi theta as the next token conditional of the base model multiplied by some exponential of the features and the parameter. So now it's clear that for any theta, you can sample from pi theta in an autoregressive fashion, and things are nice. So here's our main result in this setting. We need to make some assumptions. First, we need to assume that the optimal policy actually lies in this autoregressive softmax linear policy class. And second, we need to assume that we have a next token conditional distribution sampler for our base model. And under these two assumptions, what we show is there's an algorithm that learns a near optimal policy where the number of reward queries is what we would like. It's polynomial in the dimension and the horizon, no dependence on coverage as before. But what we've improved is the runtime. So now the runtime scales only with the token level coverage rather than the sequence level coverage. So token level coverage is just the maximum density ratio between conditional distributions of the optimal policy and the base model. And this can be generically, this can be a constant even when the sequence level coverage is exponentially large. It's like how likely are you to produce the token A compared to the base model, instead of like how likely are you to solve the Riemann hypothesis compared to the base model. So that's one good thing. The second good thing is that conditional sampling is an extremely tame condition because this is the primitive for autoregressive language models. So we definitely have access to a conditional sampler for our base model. The thing that's more subtle and basically the strongest assumption is this realizability assumption. So what this realizability assumption corresponds to, sort of analogous to in our previous setting, now it corresponds to linearity of something called a regularized value function, which I'll define on the next slide. And this is definitely a strong assumption.
Speaking of that, like for, okay, so this one, I guess it may be more rely on this, but the previous result, like for the bandit setting that you talk about, do you really need realizability, or is it possible to state the result in a more general manner that says, I don't care if the true reward is linear, I don't care if the true regularized optimal policy is realizable, I just compete with like whatever good policy in my policy class in terms of the KL regularized objective, or it is truly like, you know, you truly need that realizability assumption?
Oh, that's a good question.
I would imagine that if you do something like bonus-based exploration, you might actually need that linear reward. But when you look at algorithms like, maybe some algorithm is more agnostic to this, I don't know.
Yeah, I mean, certainly like, if you're just doing some like least squares, some simple least squares like what DPO looks like, it feels like you should get some.
But even there,
quality,
right,
but-
because you're doing this two-stage thing, first do a regression, then turn that into a policy. Like maybe even there, but DPO has this direct sort of interpretation, right? So
like you get that you get in parameter space, you get some sort of oracle inequality, where you're like not too much worse, but yeah, I guess it's, yeah, I think that there's probably some issue when you convert to the policy that
you're
the
right.
oracle inequality for the parameters doesn't correspond to for the regret. Yeah, that's a good question, if there's a way to achieve this.
Yeah, but I'm just saying, like, maybe it's worth to think more carefully about it, because I also had the impression that maybe some simpler algorithm like DPO may be more agnostic. So if you compare in that regard, like, you know, if you assume realizability, maybe you're omitting some of the advantages of like simpler algorithms.
Right. Yeah.
Because of their agnosticism.
Right. I mean, I think, yeah, I my feeling is DPO is also not gonna give it, but
right,
it could be like.
Now, give it a second thought, but I was just saying, like, maybe it's something useful.
Yeah, definitely there are other axes also, like robustness and stuff like that. Yeah. So the multi-turn spanner sampling is basically just like, it's the analog of spanner sampling, but moving from contextual bandits to the RL setting. And so it's working in this explicit MDP, which is the autoregressive MDP, where the state space is just the space of prompts and partial responses. The action space is the space of tokens, and the dynamics are defined by concatenation. So you have some string of text, you have some new token, you just add it to your state. And the regularized value function is this quantity here, which is defined as the expected reward when you roll out under your optimal policy, minus some KL regularization term. So this is the thing that we need to be linear. I don't have a great explanation for like when this is satisfied. One thing I'll say is that this is definitely stronger. It's strictly stronger than the linearity of rewards, because the regularized value function at the last step of the MDP is exactly the reward function. But one interesting question, I think, is like, are there actually like concrete settings where you might expect this to be satisfied?
Yeah. I have a question. Now you observe only a star over the trajectory, or you need to observe a Q star from the evaluator?
The evaluator only needs the rewards.
Okay, the evaluator only gives the rewards. Okay.
Yes.
Cool.
Yeah.
Thanks.
So the informal overview of the algorithm is you're sort of alternating between some sort of parameter estimation and some sort of exploration. The parameter estimation, you're doing some sort of regression similar to like what iterative DPO looks like. You're doing some sort of regression to estimate regularized value functions, which give you out the parameters. And the exploration step is kind of like similar to in-spanner sampling. You explore at the action or token level using these elliptic potentials, and you augment the distribution that you're drawing samples from using the things that are sort of novel compared to what you've seen before. I have a sort of more detailed explanation of this like alternation between the regression phase and the spanner phase. But I think I will maybe go past this in the interest of time.
One quick question regarding that, right? Because
Yes.
so you want to estimate essentially something like a Q star, right?
Yes.
But then like you're sampling from your current policy, which is not optimal.
Sure. Okay. Yeah. So maybe I'll mention this briefly. So yeah, as you say, there's some sort of error that you accumulate here, where the estimation error at some step causes some misspecification error at previous steps. And so this is sort of like maybe the main challenge is to ensure that the errors don't actually like accumulate exponentially.
Oh, so you're doing so you're doing level by level kind of a dynamic programming.
Yes.
Not from like a single Monte Carlo trajectory.
I mean, you're sort of doing like backwards to front. Like you estimate
Right.
the parameters this way, and this sort of gives you like a estimated policy to draw data from.
Oh, okay, got it.
Yeah. But it's true that the value function for this is not necessarily linear because we didn't assume that.
Mm-hmm.
So yeah, that's the regression phase, and then the spanner phase is just like drawing rollouts from the states and actions you've seen so far, and augmenting the things which are unlikely or which are looking novel. So yeah, here's just the results that this algorithm gives, is we have the sort of optimal reward complexity, and we have the runtime scaling with token level coverage instead of sequence level coverage. Now, I want to briefly mention the connection to classical RL. So some recent work from a few years ago showed that you can do RL with linear Q star if you have a state action gap and if you have reset access. You can do this efficiently. And it's known that there are some sort of lower bounds if you remove either of these assumptions. So in our setting, we have reset access because the MDP is deterministic. So you can just for free go to wherever you want in the environment. And the regularization is effectively taking place of the state action gap. So somehow it lets you, like, it sort of makes the problem like more like strongly convex, where you can bound the KL between the optimal policy and some estimate by like the squared parameter error. And the square is somehow technically important because it allows you to avoid error compounding. And this is like essentially the same observation that you need to get the fast rates in the spanner sampling setting. But I don't really have much more to say about this. Okay. And lastly, I just want to briefly mention something about improper versus proper exploration. So almost all post-training algorithms are doing something proper, where you have some model that you've estimated, you draw data, you query the rewards on this data, and then you refine your model. But spanner sampling is doing something more improper, where you draw a bunch of responses, but then you sort of carefully filter out these responses and query the rewards on some of them. And then you update your spanner. And so one question is there some algorithm that looks more like the algorithms that people actually implement in practice that achieves the same sort of guarantees? In particular, you would ideally like some algorithm that just repeatedly optimizes some loss function, draws some data, optimizes some loss function again, draws some data, and so forth. And maybe you'd hope this is more generalizable or more practical or something like that. So what we show is that actually this is not possible in our framework, which I think is kind of curious. So there's under some complexity theoretic assumption, there's no proper exploration algorithm that achieves the same guarantees as spanner sampling. So it has the reward queries independent of coverage and the time complexity scaling with coverage, but no worse.
Wait, so if you demand a proper exploration, then wouldn't it be the case that the computational complexity and reward complexity always align? Because you're not allowed to filter. Because you're gonna, isn't that saying that, is that saying that you must put a reward on every single response you
But you can do computation that's not just like,
oh, you can do more computation. Okay.
yes, like you could draw, yeah.
But
Yeah.
I guess computation here means something different, because previously, like when you say computation, mostly you're referring to like rollouts, but here it's non-rollout.
I guess computation, I always mean to be like overall runtime.
Okay.
Yeah.
But previously, I think it's the rollout that is the main sort of
Definitely dominating, yes.
thing, right? But here, you, like, they can't scale in that round. They can only scale in like, they can only increase like, you know, non-rollout related computation.
Yes. Yeah, I think maybe there's some subtlety in like maybe the framework that this rules out is slightly more general, but I don't quite remember the details and I'd have to look at that afterwards. Yeah. So yeah, there's some proof sketch. I will skip over this and just talk about like the conclusion. So we showed essentially that in our sort of toy theoretical framework, you can get this distinction between whether a good base model is necessary computationally versus statistically, and that you can get some benefits if you turn to multi-turn RL techniques and make some stronger structural assumptions. And I think this is maybe only like one small step in the direction of this very big question of how should pre-trained models be used downstream for other tasks, including but not limited to reinforcement learning. So one question in this direction is, are there any sort of ways to extend these approaches beyond the linear setting while maintaining some notion of like what is computationally feasible, what is not computationally feasible? One question is, can you make more general measures of the base model's goodness besides this sort of L infinity density ratio? And a third question is this question of robustness to reward specification. So obviously, we're not always going to have the rewards be exactly linear in the features. You might hope that there are algorithms that use fewer reward queries are like potentially more robust, but that's sort of just like a vague intuition. And it would be interesting to see like what are the sort of parameters, what is the sort of design space here. So that's all I have in the talk. Thanks for listening.
Great.
Oh.
Thanks a lot for the talk. I have maybe one question that goes along something that Nan was mentioning before. Do you think it's possible to have the C star that is at feature level, something like a expected feature direction under pi star, transpose the covariance matrix under the base model, times again the feature expected under? Because your lower bound your bounds in the tabular where the features are 1/0, but I was wondering what happens if the features are not 1/0 in the lower bound.
I believe that we have some lower bound saying this is not possible. Like we didn't write it up, but this is sort of what I recall concluding.
Because when you're sampling, like you're really relying on the the density, right? Because
yeah, definitely the analysis.
Just hit that right answer. Like the feature coverage doesn't help you at all.
Yeah.
But isn't like somewhere like in Spanner, like your guarantee somewhere the coverage shows up as feature coverage?
It was this change of measure. Oh, I mean, it shows up as the density. We use both of them basically, but we do explicitly use the change of measure.
Okay.
To like bound the sort of uncovered.
But in one of your slides, you show that if you sample enough, it is guaranteed that the feature is covered. Your spanner approximately covers the original base models feature directions. So there, I think it's feature coverage. Oh, but the complexity you need to pay is still density coverage, I guess.
I mean, you pay the density It's true that most of everywhere you have feature coverage, but handling the part where you don't have feature coverage is where you pay for the density.
I have a question. Yeah, thanks for a great talk. I was wondering about the Oracle model. So in practice, if I'm training a language model, I might have access to more than just sampling. I might have access to logits or gradient access. So I was wondering how much of this sort of coverage being necessary story is an artifact of the sort of Oracle model versus what you might see in practice.
That's a good question. I guess like we don't have great theoretical models for these more sophisticated things. Sort of the best we have is this, like, okay, you can take off the last layer or something, right? And then you have essentially you have some features. Your language model, like the last layers, you take some features, you take a softmax of those features. And so you could assume you have access to those features, and in some sense, that's what we're doing here with the autoregressive softmax linear. Like you could think of the phi as sort of the last layer, and then you're just like, what these algorithms correspond to are sort of like fine-tuning the last layer. But I don't think we have more sophisticated frameworks than that.
Right, but in that case, is it like so assuming that you're just using a simple model where like you're freezing all previous layers and you're only training the last layer. In that particular setting, I guess you do have access to the logits.
Yes, because of phi. Like phi is the logits,
Right.
I think.
Right. I guess. Yeah, I think that sort of answers my question. I guess maybe my question is like, it's probably not answerable, in a single answer. I guess I was thinking more in the sense that when you were describing the rejection sampling sort of step, I was wondering like if you have more information, maybe you could do something smarter, like maybe important sampling or something like that. But I'm not sure if that makes sense.
I think the problem there is like it's still like that part of work is doing thing like over the entire response space as a whole. I don't think any like a reasonable amount of cleverness can get over something that is fundamental. So basically, they're like conceptually what it's doing is like you generate a whole response. If you don't like it, you throw it away. Generate another whole response until something you like appears. So
Yeah,
I don't think anything like reasonably clever can handle that.
Definitely for the first part of the talk, as you say, everything's happening at a sequence level, and so there are these just like fundamental barriers. Like, in the second part of the talk, when we talked about sort of things at a token level, then like maybe you could hope to do something a little bit clever instead of token level rejection sampling. But I haven't really thought about that.
Right. Gotcha. Thanks.
Perhaps I will stop the recording in case someone wants to ask without recording.